In a previous unit, when we talked about solubility, we only talked about it in terms of how many grams of solute can dissolve in 100 grams of solvent. But today we're going to look at it through the terms of an equilibrium system, because that's what it really is. When you have a saturated solution, that means that you have a solution that's essentially full with respect to the ions that are dissolving. And you'll have any undissolved solid just kind of sitting there on the bottom. But that doesn't mean it's not doing anything. What's really happening is that you have some of the ions will dissolve, but at the same time you have some of the ions that are already dissolved crystallizing. And we're at equilibrium, since those are reverse processes. What that means is that those two things are occurring at the same rate. So we can approach solubility from an equilibrium perspective and use a K value to describe it as well. So I'm going to take a look at the solution of nickel chloride. And you can see that it's saturated. You have undissolved crystal down at the bottom. It doesn't matter if I add any more, it's not going to actually change the molarity of the solution or the concentration of the solution because, well, if you're not part of the solution, you're part of the precipitate. Now, with this nickel chloride, you can say that since that's the molarity that actually dissolves, well, since nickel chloride is going to break down into one nickel ion and two chloride ions, that the respective molarities of those ions are, in a saturated solution, 5.21 molar for nickel, and for the chloride it's going to be twice that, because you're going to get twice as many chloride ions as nickel, and you would have a molarity of 10.42. This is a very soluble substance, and you would predict that based on our solubility rules, as chloride dissolves with pretty much anything besides some of the heavier metals, not including nickel. Now, when we're writing this out as a K expression, we have to look at what the actual equation is for the dissolving of it. So nickel chloride, that's a solid, dissolves into nickel, the aqueous ion, and two chloride aqueous ions. Since the solid, and we saw that it doesn't matter if you add more solid, the amount of it actually doesn't impact what dissolves at all. Therefore, we can leave that solid out of the K expression, and all we would say is that our K value is equal to the nickel concentration and the chloride concentration squared. So if we're establishing what the KSP for this would be, all we have to do is plug in our concentrations. So for nickel, it's 5.21 molar, as we had already stated, and for the chloride, it's 10.42 molar, which we already stated. And we have to square that value. And we end up with a very high value for K, which is what you would predict for something that's very soluble. So our K value for this, based off our molarity of what dissolves, is 565.68. So now that we've looked at establishing KSP from the molarity of a saturated solution of a compound, we can also go in the other direction, where we can use the KSP of a compound to figure out what the concentrations of the ions will be in a saturated solution. So we're going to look at a much less soluble compound, calcium fluoride, in this example. So what I want to do is determine the concentration of both the calcium ion and the fluoride ion that will be present in a saturated solution, which means it's at equilibrium. So the KSP for this substance is 5.3 times 10 to the negative 11. And just writing out what the K expression would be, since it breaks down into two fluorides and one calcium, you would have calcium concentration times the fluoride concentration squared. So what we need to do is set up a Rice table to kind of show how we're going to solve for those values. So again, since calcium fluoride is a solid, it doesn't matter how much you have. It's not going to impact the concentration when it's once it's already saturated. We know that it's going to go down by some value, but at the end it really doesn't matter what the concentration of it is. However, for the calcium and the fluoride ions, for each one of these that breaks down, you're going to get some amount of calcium, and you're going to get twice that amount of fluoride. So we can represent these values as X for calcium, and then 2X for the fluoride ion. So at equilibrium, you're going to have a concentration of calcium represented as X, and fluoride will be twice that value. So then what we have to do is come back to our KSP expression and plug those in for concentration. So calcium is X and the fluoride is 2X. And so that should be squared on the outside. And what we end up with is that our KSP is equal to 4X cubed. Simplifying that a little bit by dividing both sides by 4 gives us this expression, and then solving for X by taking the cube root, you would see that we get a value of 2.36 times 10 to the negative 4th to represent X. So if at equilibrium we use X to represent calcium, that means our calcium concentration is going to be equal to what X was, which is 2.36 times 10 to the negative 4. And since the fluoride ion concentration is going to be twice that value, we can say that the concentration of fluoride ions in a saturated calcium fluoride solution would be 4.72 times 10 to the negative 4. Now, one other thing I want to talk about with respect to solubility and ion concentrations, we're not actually going to have to quantify, but what we're going to have to look at conceptually is Le Chatelier's principle through something known as the common ion effect. So Le Chatelier's principle states that when a stress is applied to an equilibrium system, the system is going to try to alleviate that stress by shifting in one way or another. And the common ion effect essentially states that when a compound containing one of the ions that's involved in a saturated solution is added, well, it's going to increase the concentration of that ion, and it's going to make some of the solution, some of the dissolved ions precipitate. And vice versa, if you have something that precipitates out some of the ions that are involved in a saturated solution, it's going to cause the equilibrium system to shift in the favor of making more of the stuff dissolve. And what I mean by that is, if I added, and this says saturated solution, if I added something that contained the fluoride ion, say sodium fluoride, I'm going to increase this concentration. And since the K is a constant value, if this value goes up, then that means this value is going to have to go down as a result. And the only way the concentration of the calcium ions could go down is if some of it precipitates out. Also, if you added something that would precipitate some of the calcium and drop this concentration, since this is a constant value, the only way to get this product to equal that value is for more of the undissolved calcium fluoride ion to dissolve. So that's the common ion effect and how it affects solubility. You're not going to actually have to quantify what adding those things or subtracting those things would do and what the concentrations would be. We could, but we're not making you responsible for that.